the RESCON model with a set of data that Nikos mentioned, a theoretical formulation as well as some demonstration. Today, I think he will elaborate later about the focus for today. So we expect all the participants to participate actively like they did yesterday. It was a really impressive session yesterday, so that we can maximize the learning from this training platform with the person who is developing the model is with us as a resource person. With this very brief welcome note, I would like to hand over the session to Dr. Nikos for the rest of the day. And also I will be posting the answer to the questions posed yesterday in our chat box. Some were answered yesterday, but some were we could not discuss, but Nikos has already answered them. I will post that in the chat box and he will be taking them on along the way at appropriate time. Thank you and enjoy your time. Nikos, over to you.
Okay, thank you very much, Professor Pandeyji. Let me share my screen. Okay. So we continue the second day of our training on RESCON 2 together with ISMOD and the World Bank. And first of all, today we'll do a very short recap of the first day. And then we will focus on hands-on sample training with focus on storage reservoirs. We will, first of all, we will build on the sample that we shared yesterday. It is included as demo project file in the folder that was shared by the organizers for this event. And our main concern today is that we go together through that sample. What I would like you to do is that you change the different parameters related with implementation of sediment management, and then we discuss the results. What I would like to do today is that we focus on the interpretation of the results and see what is the physical meaning. So if the reservoir lifetime of is increased because we have a more aggressive drawdown during sluicing, what is the reason behind this? So we will see also the climate change analysis. We will discuss a lot, and we will go together how can we retrieve the necessary data for this and how they can be introduced into the model. We will discuss also calibration and with different data, what are the possibilities in RESCON. And of course, I'm looking forward to an interactive session with questions, which I hope that I will be able to answer. Please feel free to interrupt during the session today. If there is a question, a topic that you would like to discuss. I will try also to do this as interactive as possible by actually asking you questions, and everybody who feels that would like to respond, feel free to do so. Either by raising hand and through your audio, or by posting in the chat box. So to start with, let's try within 5 or 10 minutes maximum to go through what we saw today. I will use actually the same presentation. And first we discussed so how the reservoirs provide regulation of the naturally variable river flows, why sedimentation is a natural enemy of reservoir storage, and what is the global trends with regards to storage loss due to sedimentation. We discussed about the impacts of sedimentation on environment, economic performance and safety of reservoirs and dams, the relationship between climate change and water, not only availability but also variability. What is the combined effect of sedimentation and climate change? We said that actually climate change will magnify, will exacerbate the already adverse impact of sedimentation on the performance of reservoirs. And we discussed very briefly about the available techniques or methods or strategies to combat reservoir sedimentation. We discussed about the reduction of sediment yield, sediment routing techniques, and deposit removal techniques. A very short presentation of the global sediment management study that was conducted by World Bank with funding from the Austrian Ministry of Finance, whereby RESCON 2 is a knowledge product of this study. What are the objectives of RESCON 2, which is mostly a preliminary screening of the state-of-the-art sediment management alternatives at early project development phases when we have limited data? What is the theoretical background? A possible source for resources on sediment management, the International Sediment Management Network HydroSedNet, which is freely available on the web. What are the limitations, where we said and clearly indicate that it is not a numerical model, so it is based on empirical equations and requires limited data. The philosophy is to apply this at the beginning of a project in order to gain a first idea on the risks related to sedimentation and possible sediment management countermeasures. The timeline, what are the questions, where we start with the basic question, okay, what is the lifetime if we don't do anything? How can sediment management improve things for the historic climate? And of course, how can sediment management improve the resilience of the facility, build resilience into the system? There's capabilities with focus on sedimentation prediction, evaluation of sediment management alternatives, the economic appraisal, and the climate change analysis. We described the flow chart, the different steps for the assessment of the physical performance of the reservoir as well as economic performance. We gave an example to showcase how the extension of the reservoir lifetime can improve the economic performance of the reservoir, as well as to showcase that actually also we must consider always that sediment management comes also at an additional cost that must, of course, also be considered in any analysis we perform. We discussed about the different types of water yields that can be provided by the reservoir depending on the requirements for flow regulation. So we discussed about the different types of discounting which are available in order to give value to the future benefits. Again, about the climate change analysis and how sediment management can provide an adaptation to anticipated non-stationary climate conditions in the future, and the hydrologic response of to changes, anomalies in temperature and precipitation. A source for the climate change data, a very short indication how we can see what is the sensible range of the economic performance of the reservoir to different climate futures, which are predicted by the global circulation models. And this can be considered to be sort of a climate stress test for our reservoir to climate change. So all in all, that was what we discussed yesterday. Then we proceeded with a demo example where we will build also today. We said that the main questions that we have is what happens if no sediment management is applied. And this is where we said yesterday. We saw how to interpret the plots that are generated in RESCON for the sedimentation prediction. And now we will see how we put the input for the economic appraisal for the revenues assessment, and we will interpret also the respective results. After this, I would like you to also open RESCON 2, import the demo file that is included in the training folder, and together we will work on the evaluation of the sediment management strategies. So, turning back to RESCON, first let me just import the sorry, need to find the demo project. So here we had 6.2 million tons per year sediment inflow. If you recall the slide that we had with the presentation of the sample where we are working, and actually we described the input for the cost assessment, and we discussed about the abrasion risk assessment, and we were on this slide where we are giving the input for the assessment of the revenues generated by the reservoir. So we discussed also about the environmental appraisal, so I will not go into detail at this point here. So after this presentation of the revenues, I would like that we go together through the sediment management alternatives. So to complete the presentation of the basic input, let's call it this way, so the input that is needed to run at least the no action scenario. So first you see we have two main groups. So one is the water uses and the water yield evaluation. Here we have the priorities, of course, are fixed and ranked. We start with the most important priority. The second, we can give up to 4 water uses, and we can select among municipal and industrial water supply, irrigation, storage hydropower, and daily peaking hydropower. Please note that the run-of-river hydropower, the non-dispatchable hydropower or the non-dependable hydropower is automatically calculated. I will explain how this is done. So here in this example that we are showing here, so we have 2 water uses. The first priority is daily peaking hydropower, and the second is irrigation. The next step is that we must specify the required reliability for the water uses that require long-term regulation. In that case, irrigation. Here in that case, we have seasonal regulation that is performed, and we say that we must have a reliability of 90%. So that means 90% of the time the reservoir must be able to provide the specified demand, which in this scenario corresponds to 40% of the mean annual flow. If you recall in the presentation, we discussed about empirical equations that are used for the assessment of the firm water yield and the interrelationship between reliability, storage availability, and hydrologic variability. These are the 3 key parameters, and another parameter that plays a role is the statistical distribution of the incoming flows that is introduced also in the empirical equations for the assessment of the firm water yield. When we say firm water yield, we mean so the reservoir that the water yield that the reservoir will be able to provide for this, in that case, 90% of the time. Here you see that the fields for reliability and for demand for daily peaking, so they are great. So that means we cannot insert here any input. So the reliability actually for daily peaking is considered so that every year the reservoir will be able to provide the necessary peaking operation, and the demand is automatically calculated based on the features for hydropower that can be specified here down. So you see this box named hydropower. So now you see if I put here, for example, M&I water supply, then these input boxes can be modified. And the reason is that this water use is dependent on reliability, and it is assessed with the empirical equations that we discussed. So Gould-Dinser method if we have over-year behavior, or Curry and Fogel if we have within-year reservoir behavior. So let's go back to that example where we have daily peaking hydropower, because I would like to show you that, look here, what we are specifying is that we have a gross head of 130 meters. Our power station must be perform peaking 800 days per year with a peaking duration of 9 hours. The installed capacity in our per day. The installed capacity of our turbine is 180 megawatts, and the capacity factor is close to 40%. Now the question is, what are we doing with this information? Why we need to specify this information? First of all, based on the gross head and the installed capacity, we can calculate the design discharge of that is required in order to produce the 180 megawatts. Then, based on the installed on the design discharge of our equipment and the duration of daily peaking of 9 hours, we can calculate what is the water demand for the peaking operation. And then, based on the number of daily peaking cycles per year and the calculate amount of water used daily for peaking operation, we end up with this water demand for daily peaking hydropower of 50%. So this is internally calculated. Now, if we see here this plot, what we see is that we have also the dark blue colored bars, and this is the non-firm hydropower. By specifying the capacity factor, we can calculate the total energy that is mean annual energy that is produced by our power station. So now we have calculated also, we can calculate also how much is the peak energy that is generated. And so intrinsically, automatically, we assume that the remaining between calculated mean annual energy and calculated peak energy is non-dependable variable run-of-river hydropower. So this is also introduced into the revenues assessment. Apart from this, this graph here, what shows us is that first of all, okay, we have a demand for ecological flow of 10% that must be released downstream. So we have the demand for the water demand for the peaking operation. Then the second priority is the irrigation, where we have the dependency on storage starting earlier because we have this reliability of 90%. And then last is the variable run-of-river operation. So if we change here the irrigation, say we want a demand of 99, so actually we have a small drop of the firm water yield. So we have this small drop of the firm water yield for irrigation that can be provided exactly because we increased the reliability. So you can imagine, so here we have So we have the storage here doesn't change. Now I'm talking about this specific bar here. And we say that we want a more reliable water supply for irrigation. So that means, and we don't change other parameters. So that means the firm water yield must be smaller. As the required reliability increases, the water yield for this reliability that can be provided by a given reservoir and for a given hydrologic variability drops. So this is the behavior that we saw here. Also, if we increase the duration of daily peaking, say we do this 12 hours, then what we see is that the water demand for peaking increases, and we are not able to produce variable runoff river, and also the demand, the firm water yield for irrigation, now it is affected by the water demand for daily peaking. Okay, so these are things that we have been trying to resolve in the meanwhile. So what you saw just right now. Here, what we see is that the peaking operation will be affected by storage loss, that we see here on the horizontal axis, when the storage loss exceeds approximately 90%. In this case, we have a relatively large reservoir, which the reason is that it is used also, it is a multi-purpose reservoir that is used also for irrigation. At this point, so we will have the reservoir capacity will reach a level where actually it will not be possible to store the water that is needed in order to satisfy the peaking operation with duration of 9 hours. So this is why we see this drop here. And of course, at this level, we will not be able to provide any regulation to satisfy the demand for irrigation. So here, this is just an indication how the extension of reservoir lifetime and conservation of reservoir storage can actually protect the different beneficial water uses. So enough with this. Here, what we see is the unit rates that we need to specify in order to monetize the calculated water yields into revenues. So since we have a hydropower use, you see that we have to specify the tariff, the cost in dollars per kilowatt hour for non-dependable, non-firm hydropower production. This is the dark blue color. And for the peak hydroelectricity. So as expected, peak hydroelectricity is more expensive than is sold more expensive than the dependable runoff river. This, of course, depends on the power purchase agreement that is conducted and the legislation in the countries. We have also a different unit rate for the irrigation, for the irrigation water yield that is applied by the reservoir. And here, so this is just indicative. So it's important to point out that so this map here gives some indications on costs for agriculture, domestic and industry water in different countries. This information is outdated. Actually, it was included in the manual of the first version of RESCON, but it is used to provide an indication of a range of values if this information is not available at early project development phases. Of course, inflation, so the change of the conditions must be considered. So, but this aims to provide support during the setup of the model and the preparation of the economic appraisal. So much to the input of revenues. Then, if we go to results, let's go to the second row here on this dashboard that we have. First of all, we see again the same plot that we had earlier. So how is the allocation of the water yield to the different water uses? Then, based on the specified unit rates, we see what are the revenues from the different water yields for the different beneficial uses. And then here we see the long-term economic performance, which is the sum of the annual net present values that have been calculated based on these annual revenues for different discounting concepts. Here we are using, so you see that, the economic analysis shows that the aggregate NPV is $215 million. We see that this is our main scenario. So the classic exponential discounting, which, if I remember correct, it was performed with a discount rate of 3%, which is specified here. Now, so from my side, I think that we have seen how we specify the basic input. Now, if we go to sediment management, this is where I would like that we work together, that you will open RESCON, you will import the demo file that is included in the training folder, and then we discuss together how we can assess the different sediment management alternatives. First of all, I understand that we had a problem with MacBooks with the installation of the software. This will be resolved, will be communicated to the programmer, so it comes as a surprise, but I guess so that the solution is easy. I understand that Windows 10, Windows 11 and older versions, we are okay. So if you agree with this approach, I would suggest that I close here this. Let me start again RESCON, and so I will do import project data. I find the demo project and I open this. Please let me know if so far so good. So if there are any issues, please raise hand at this phase, because this is an important step, so that everybody, so apologize for the MacBook users, the Windows users are able to see the screen that we are looking here. So I understand that you are okay.
Nicholas, can you repeat once?
So how we import the project
demo
file?
Yeah, how you import the demo? Yeah.
Okay, sorry. So I close this again. So we open RESCON. You see the screen?
Yes.
and we go File,
Yeah.
Import Project Data.
Yes.
Then you should see something similar to this. So I choose now the location where I have the training material. And I open the demo project,
Yes.
JSON file.
Okay. Okay. Thank you.
Okay, perfect. Okay, so then you should see the geometrical features of the reservoir, hydrological. Please go into sediment and change the mean annual total sediment yield from 4 to 6.2. So now when we go into results and no action, you should see more or less these results. So a lifetime of 38 years, a long-term storage capacity of 0%. So here, I have the measured storage development. So the measured storage development is shown with the bars, and the calculated is shown by the lines. Please note that here this is an old example, so this is with, I think, with 4 compartments, so don't remember. So generally what we see is that we have a good agreement between gross storage development. We could follow relatively good the development of the active storage. And now, oops. Okay, and now look, so we are at 25 here in this plot. So the reservoir was commissioned in 1988. We have 25 years of operation till the latest bathymetrical survey, 2013, in this example. So after 25 years of operation, the gross storage was approximately 40 million cubic meter, and the active storage was approximately between 20 and 25 million cubic meter. So now if we go into RESCON, and after 25 years of operation, so we have a storage of approximately 40 million, is somewhere here, and the calculated active storage is a little bit higher than 25 million. So this shows that this is a relatively good approach of the assessment. So here what I would like you to do now is go back to input, go to sediment and try to see if we change the trap efficiency method, how this affects the results. And actually, this is one method that we have for the calibration of the model. So I would like you to run, again, this no action assessment with the different trap efficiency methods. In the meanwhile, I have received some comments. I will reach out to the participants who are facing some problems. So I would suggest that we give 10 minutes or 12 minutes so that you try to change the trap efficiency calculation or change other parameters like the mean annual sediment yield, and try to see how this affects the assessment of the reservoir lifetime.
Because I think we are going fast. Can if we follow step by step, one at a time, it will be more easy for us to follow.
Okay. So I would suggest let's start with the trap efficiency and try to see if we change from local to upstream, what happens, and then let's try to discuss this behavior. Is this okay?
Lifetime has been increased to 48 years.
38 years, yeah.
48, from 38 it went to 48 years.
Mm-hmm.
And the long-term storage capacity is still 0.
So let's try to explain this behavior. So this is with the local curve, the first that we saw. And this is if we use the upstream. So okay, first let me anyone who has an idea why we have this different assessment of the lifetime? So we will need to go here on this plot on the trap efficiency. And here what we see is on the vertical axis, the trap efficiency. On the horizontal axis, it is called the sedimentation index. So generally consider that this, the sedimentation index, it is a property of the reservoir. So if we have the same value, that means we are having the same condition of the reservoir. So say here we are at this point. So when we compare the two curves, the red one is the selected always. So we see that for this value, actually 10 million of sedimentation index, so the calculated trap efficiency is lower for the upstream curve than for the local. For the local is close to 70%, and for the upstream it is close to 35%, so half trap efficiency. So this means that if we use the upstream curve for the trap efficiency calculation, the reservoir is able to retain, so the calculation shows that the reservoir retains less sediment. So this means that it will take more time to get the reservoir filled with sediment. And this is why, so the calculation with Churchill upstream curve gives longer lifetimes of the reservoir.
How do we decide which curve is suitable for our reservoir?
So our experience is that both methods, Brun and Churchill, they are widely used. So they are old classic methods for the assessment of reservoirs. Generally, Brun gives a good estimate of the average trap efficiency over longer time periods. Churchill trap efficiency is used for reservoirs that are regularly sluiced or we have alterations of water level. So this is one criterion. Generally, Churchill has the advantage that it considers both the residence time of sediment in the reservoir. So the residence time is the storage capacity expressed in million cubic meter divided by the mean annual flow. So cubic meter, million cubic meter per year. So you see that we have it is expressed in years or can be expressed in seconds. So this is the time that water, the same, say, molecule of water, will spend in the reservoir. This is the time that a sediment particle has to decide if it will remain in suspension or it will drop out of the water column. So this is why it is an important parameter for the trap efficiency calculation. So this residence time is introduced in both methods, Brun and Churchill. But Churchill considers also a second parameter. This is the mean flow velocity in the reservoir. So that means it not only considers how much is the available time for the sediment particle to drop out from the water column, but also considers how fast a sediment particle on average travels in suspension out of the reservoir, within the reservoir. So this is an additional parameter. All in all, the key conclusion. My personal experience is that with Churchill, so we have good first estimates. We have both curves because they are the classic approaches widely used worldwide. And because here I see in the chat box, we have seen the different lifetimes. This can be used as an important calibration parameter. So, okay, especially sediment transport, we have high uncertainties. It's always good to have measurements, and if they are available, then the best method forward is to see how the results, what methods brings the best agreement between measurement and measured storage development. Now, the other important parameter is that we have for Churchill two curves, local and upstream. And for Brun, we have upper, median, and lower. So this actually is related more to the size of the sediment particles arriving at the reservoirs, the grain size distribution. So the upper curve of Brun is for coarser material. The median is for average, let's call it this way, material. and the lower is for finer material. All this is relative, so I don't have to give you here absolute numbers. So if you expect that you will have coarse material entering your reservoir, so for instance, if there is a big number of landslides upstream, perhaps a good first approach is to try to use the upper curve of Brun. If you have a big reservoir upstream of the reservoir you are studying, this means that the coarser part of the particles will be retained in the upstream reservoir. The sediment releases from the upstream reservoir are expected to be finer material. In that case, use the lower curve of Brun. Again, you see that for the same condition of the reservoir, the lower gives here for a capacity inflow ratio. This is the residence time, so of 78%, and the upper curve gives a capacity of 95%. So the lower trap efficiency is an indication of finer material entering the reservoir and longer time periods. So this, I would say, that are the criteria for the selection of the upper curve. And to summarize, consider this to be a calibration method if you have available measures, available measurements for an existing reservoir, or if you are studying a greenfield project and nearby is an existing reservoir, you could set up a first model for the existing reservoir, see what trap efficiency method works better, and then try to transpose this assessment also in the reservoir that you are studying, the greenfield reservoir. If there are no measurements, the logical considerations is if you have generally a dynamic reservoir with significant alterations of the water level in the reservoir, regularly sluiced reservoir, then I would suggest to start with the Churchill equation and then go to Brun. And if you have upstream retention of sediment, try with the lower curves that you see, here the lower or the median for Brun, or for Churchill, the upstream. I hope this answers the question, and actually this was also one of the questions we received yesterday that we didn't have time. Please let me know if you think so that this covers.
Yeah, Nicholas, thank you so much. We have a couple of comments and a query. So Subhas Thapa asks whether it is possible to view the graphs independently.
What do you mean?
The graphs you can see, can we view the graphs independently, like individual graphs?
For different, the results for different, so to see.
Yes, for different
the
parameters.
Results for different. So in that case, what we are using, we go to results, export to XLS sets. So we write here, now I don't remember, so I think it was Churchill, say now what I would do, Churchill, local, no action, and project, the demo project, so that I don't lose track. And I would save this. And here you see we have the calculated storage. Okay. And then what we would need to do is go back to input, sediment. Sorry, it was upstream what we had. Then we go to results. we must calculate first. So the calculation is repeated when is performed when we press results. And I would go to results, export to XLS. So I will think upstream. And then this way we can compute, compare the results of different calculations, even if we are talking for the same scenario. So that means no action, but we want to compare the different results. We will need to generate this Excel file in order to save the results. And then we can, that was our thinking. So because there are really so many parameters that can be changed. So we export this in Excel, and everyone can generate any graphs he thinks would be useful for the type of analysis he or she is conducting.
Yeah, thank you, Nicholas. That was really helpful. I think the others are just brief comments. I'm not sure about the Bharat Paudilji. There is no annual sediment yield showing in sediment section of input.
Could you perhaps, would it be possible to share your screen to have a look on this? Because I'm...
Oh, let me share. Or Bharatji, can you, the issue is resolved.
It is resolved, okay.
Yeah, the issue has been resolved, yeah. So I think, yeah, back to you, Nicholas.
Just because I'm interested also in this feedback. Is there perhaps any idea what was the reason for the initial response and how it was resolved? Because
yeah, Bharat Paudilji, can you unmute your mic and discuss the issue?
So previously I was I was logged into sediment management section, so I couldn't find in that section.
right.
So that I used sediment section after that.
Okay. And Darsan, I see that there was Darsan. Are you okay? So Darsan Arial.
I don't see his comment in the chat box.
Okay.
Darsanji, are you online? Can you just unmute your mic and discuss the issue?
Hello?
Hello? Yeah, we can hear you.
Hi, Darsan.
Right, so it did not work on my Windows 10 device, though I think that might be because I have an AMD chipset. If anyone else has an AMD device and it does work for them, could you please tell me?
No, this should not be an issue. Actually, I think I have an AMD. So...
then I guess it's something else.
Darsan, hope I'm pronouncing your name correct. Let us on the first occasion, perhaps to chat, would like to see. So what is the problem so that we can resolve this?
Well, I did try to get the file working. I downloaded it and then extracted the file, after which I tried to open the UI.exe, however, nothing happened. There was a slight blue circle around the mouse. Other than that, nothing happened. I updated my Java. There was no difference. There was just the file itself just didn't open.
Okay. So your Java, okay, Darsan, so that we can continue, I will reach out to you to see and to see if there is something that we can do. So, and what might be the reason.
Nicholas,
right.
Could I speak?
Yeah, of course.
I want to mention that in our trap efficiency COP, I don't have the option of median. There is lower there is lower upstream and median, but median option I cannot select in my case. And another thing is in a annual sediment yield, the words or the options are overlapping.
This has to do, I think that you would have, you are using so a small screen. So in your laptop, could that be the case? So in that case, let me show you how you can do this. So you do right click on the desktop, and then you go to display settings. And then you can change the display resolution, for example, or the scale. And this way, so you won't have this issue with the overlapping. The reason was that we need to have a minimum size of the screen. And if the monitor
What should
you're using...
What should be the resolution, Nicholas?
Mm-hmm.
What should be the resolution I have to select?
Okay, yeah. So the maximum resolution. Okay.
Yeah.
Mm-hmm.
Yeah,
Okay.
I think, yeah.
So now I would like.
What about the option of median in COB, trap efficiency COB?
Sorry, with this, so perhaps you are on Churchill. Make sure that you are on Brun. And there should be three options: the upper, median, and lower. So now, really, that you see the upper and the lower, and the median does not appear. Please make sure that you are on Brun.
Okay, thank you, Nicholas. Okay, I'll try it.
Did anybody else so see
So
this?
No, all good now. So back to you, Nicholas, to proceed ahead.
Okay.
Thank you.
So let's go to sediment management. Sorry, let's use. So look, now I have Churchill and upstream as trap efficiency, because we saw that this way we approach the measured storage development. We have the best possible agreement with these options for trap efficiency between measured and calculated storage. So please set as trap efficiency Churchill and upstream. And then let's go. Sorry, my mistake. Sediment, Churchill, and local, because we have no retention upstream. So we have the 38 years lifetime. Let's go back to results. Let's go to sediment management. And now here, first of all, you see that we have this orange bar here. Okay. So this shows that there is a mistake somewhere. Then we see that we have catchment management, orange, and tracking, orange. So that means the input that we have now in our project file are okay, but there is a mistake in catchment management and in tracking. First of all, and then we see that here we have a mistake at the realization time lag for structural measures. So now, this is my question for you. You remember we calculated a trap efficiency of 38 years, correct, for the no action scenario. And we see that this 5 that we have here, it is wrong. Any explanation why this is considered by the model to be wrong? All right. So look, we said that the reservoir, if we don't apply any sediment management, will have a lifetime of 38 years, correct? And here what we are specifying is that implement structural measures after 36 years, but the impact on sediment yield reduction will be realized 5 years after implementation of the measures. 36 and 5 makes 41 years. So that means what we are doing here is we are specifying a sediment management strategy which will become effective after our reservoir is totally full with sediment. So this doesn't make sense. Why should we want to reduce the sediment yield arriving at our reservoir when we actually don't have any reservoir? So for this reason, if we do this one, I hope it will work. So you can see that then we can proceed with the calculation of catchment management. So here now let's go to catchment management. What we can do. First of all, we need to specify what is so Sanita, we will come back to you. So what we need first of all to specify is what is the reduction in sediment yield that can be achieved through different nature-based measures or structural measures in the upstream catchment. Please note that this is actually the result of a separate assessment that needs to be performed. It requires modeling of the upstream catchment, assessment of the surface erosion, assessment of the efficiency of different measures, for example, reforestation, terracing in steep valley slopes, so construction of check dams to break the slope of steep tributaries, small tributaries, and so on. So this should be separately assessed. So it cannot be, of course, with this input assessed by RESCON. But what you can do here with RESCON is, the idea is, you can set a target here for the efficiency of catchment management measures. You can see how the reservoir reacts to different sediment yield reduction scenarios. Okay, and then this way this can be a preliminary assessment for the target efficiency of the design of catchment management measures. So what I want to say is that this is a possible analysis that could bring together the performance of the reservoir and the performance of the catchment management measures in the upstream catchment by assessing what is the impact of the first of the measures on the performance of the reservoir. I hope this is clear. So, and as a first step, try to think that actually we cannot expect so a very so to achieve a reduction of the sediment yield, say of 80% through catchment management measures can be achieved only if we have a very degraded upstream catchment, and we go very aggressively with different measures. Okay, usually if we have an upstream catchment in a normal condition, then so based on publications, we can expect a reduction of suspended load of 20 or 30%, and with bed load, depending on the type of measures, we can expect a reduction of 20, 50%, 60%. So what I want to say is don't expect that you can really minimize the sediment inflow. But what you have to keep in mind is that this depends on the condition of the catchment. If we have a catchment without any vegetation, then if we make a reforestation, of course, this will have a very significant impact. But if we have a catchment with different land uses, where we have forest, where we have agriculture and so on, so then, of course, not 80%, but we can expect a reduction of the sediment yield 30, 40%, 20%. This depends on the extent of the catchment management measures. As said, this is a separate analysis, and here what we are doing can help to bring together the two different types of analysis. One is the reservoir, the other is the measures in the upstream catchment. Then we need to implement a rough assessment of the respective costs, and then we can implement the implementation schedule, needs to be specified. Okay, and here you see a first assessment regarding optimization. So here the different colors show the economic performance of the reservoir for different catchment management schedules. And here what this plot shows is blue here is a better economic performance, red is a worse economic performance. The earlier we start with the implementation of catchment management measures, the better the long-term economic performance of the reservoir. Okay. So what I would like you to do is to try to play with different implementation years and implementation schedules or efficiencies and see what is the reaction of the storage development and the economic performance of the reservoir.
Nicholas, in the meantime, when we are working on this, I have a query for you from Vivek Kushal. So he's asking, is it possible to apply measures taken in similar catchment in case of unavailability of catchment sediment interventions?
Is it possible to apply measures taken similar? Vivek.
Vivekji, are you there? I don't think.
Yeah. Vivek, perhaps to elaborate a little bit on the question.
Yeah.
Okay.
Vivekji, are you there?
Look,
Hi,
I
Nicholas.
think, yeah. Hi, Vivek.
What I was trying to ask is, if we have applied some intervention measure in a catchment of similar topography or geology, then we can take the results from that catchment and apply some data from that catchment to formulate our sediment management measure in the catchment on which we are modeling.
Yeah. So, and as a first step, this can be very useful if there is relevant information, even from other comparable catchments. So you mentioned topography and geology. One important parameter is also land uses. So if you would like to somehow see the similarity between catchments, and especially for catchment management measures, consider land uses too. So since, of course, area used for agriculture is more prone to surface erosion than forested areas. So this is something that I would consider. And again, as a first approximation, you can see, okay, if I have more forest in one catchment, actually than in another, actually I can expect that catchment management will be more effective in the area with more agriculture, because exactly so this is what we were discussing. So it depends also on the status, on the condition of the upstream catchment. If your catchment is more susceptible to surface erosion, then also catchment management measures will be more effective in reducing. Consider that we are always talking about relative numbers, not absolute numbers.
Yeah. Thank you.
Suman, I see one question. So if contour plot is compact or nearly spaced, perhaps is it possible to share screen to?
Sorry for the question, Nicholas, or by Suman?
See, there is a question by Suman.
Yeah, okay. Can you see my screen?
Give me 1 second. Where is it? Sorry, somehow I'm struggling with Zoom here. Let me perhaps, I'm stopping. No, actually I can't.
Okay. Suman, if you can come online and explain your question, because I can't understand. This is technical for me.
Wait, sorry. Sunita, can you perhaps share again screen? So I think I can see now your screen.
Yeah.
Had to stop sharing my screen. I would like, if possible, to have an example. So to
Sorry,
have an example of this contour plot,
Mm-hmm.
so to understand what with compact. I agree. So perhaps sharing a screenshot and perhaps sharing the chat box. So that's a good suggestion.
Yeah. And we have another question from Dilkumar Raiji. Can we apply this model to both older and newer dams?
So the model can be applied both in existing and greenfield projects. So with existing, we mean old dams, and with greenfield, we mean the dams that are under design, in the design phase, and have not been constructed yet.
So, Kumanji, if you can share your thought, or please come online to explain you. Otherwise, we need to move ahead.
Hey, Dr.
Okay.
Nikos, may I ask
Yeah.
you one question?
Yeah, of course.
Yeah, my name is Subhas. Okay. So,
Hello,
so
Subhas.
far so good. I am following up quite well. So regarding the catchment management, when we increase the expected efficiency, we can clearly see that the years of operations becomes greater.
Mm-hmm.
And likewise, if we start the nature-based measures as well as structural measures well before time, then I think the cost, regular annual cost and catchment management cost are also lesser, and the lifetime of the operation of the reservoir also increases.
Mm-hmm.
My question is, in the Himalayan rivers, especially in Nepal, where we also have to do preliminary studies of storage projects. Maybe you know the conditions of the Himalayan rivers, mountain rivers, very sediment-laden rivers. So what would be a very relevant figure of the suspended yield reduction efficiency and bed load yield reduction efficiency, so that we can also run the model quickly and bring a very effective evaluation? So do you have any idea that you can suggest? So what would be the figures that would be very suitable for Himalayan rivers, especially in Nepal? Like
this is, I understand the point of your question. This is difficult to assess, takes additional studies. Look, the steeper the slopes, the more difficult to implement measures in the upstream catchment. I mean, in Nepal, first, okay, there are also milder rivers with milder slopes where you have also more agriculture. So there perhaps is catchment management could be more effective. But when you go up in the Himalayas, I mean, the conditions favor the generation of sediment, of course, and there are processes which are difficult to control. I cannot give figures, even indicative. This is something that needs to be assessed with separate studies. What I can say is that, again, speaking in relative numbers, you can expect that, okay, so if you have more agriculture in your catchment, roads and so on, then catchment management measures can be more effective. In the steep slopes, one thing that should be considered is that so in any case, catchment management measures are needed. So if you have construction of new roads and so on, this might affect also the sediment generation. It's very important to plan the respective mitigation measures. For example, correct drainage of road network, slope stabilization measures. So don't leave sediment without any erosion protection, reforestation. So measures that will not can support the stabilization after measures that are taken in steep slopes. Subhas, sorry for not being able to provide more specific information in terms of absolute numbers.
Yeah. Thank you, Nicholas. I think we have less than 40 minutes now, and we would like to continue with your lecture.
Okay.
Yeah, thank you. Back to you.
So I think that Subhas summarized well the key takeaways, so that of course, if we have more aggressive catchment management, so we will have a longer time period, service lifetime of our reservoir, and the economic performance depends largely on the implementation schedule. And so here we see that actually the earlier we take action in the upstream catchment, the better is also with regards to economic performance of our reservoir. As a next step, I would like that we go to dredging. Look, on purpose I gave this and I changed this sediment inflow from 4 to 6.2 because I wanted to show the calibration, and as well as show the mistakes that are created in the model and how they can be identified. Here we have also again a same mistake in tracking. If we do this 10, then tracking of course is implemented before the full sedimentation of our reservoir. So this resolves the problem. Now let's go to dredging, and keep in mind that the analysis is very similar to tracking. So with dredging, we have two possible questions that we can answer, or we have two answers to two possible questions. So the first is, what is the amount of sediment that we can remove, that we must remove with dredging from our reservoir in order to have a sustainable reservoir? And here, this is the question that we are asking by setting these combo bots to sustainable solution with technical constraints. The other question is, what will happen to our reservoir if we remove, sorry, not 32 million that we have here, 3.2 million cubic meter every year? Okay, then the other input that we give is, okay, when will we implement dredging? First, we need to say when we will start with dredging and how often we will perform dredging. Here, what we see is that we will start after 15 years and we will perform dredging every 1 year. Now, think that if we say that we will perform dredging every 5 or every 10 years, intrinsically, this would mean that actually the operator will outsource the dredging activity to a contractor. Okay. If we say that dredging will be performed every year, this would mean intrinsically that actually the operator will procure dredging equipment and will perform dredging himself. Here we need to specify the costs. They depend on the type of dredging, if we will have hydraulic or mechanical. Keep in mind that generally hydraulic dredging is usually applied in reservoirs. An important aspect is, what will we do with the dredged material? Will they be placed downstream of the dam through a pipeline, or will they be pumped to upland disposal areas? Here, think that if we go to upland disposal areas, practically this is a non-sustainable solution, because we will remove every year or every 10 years an amount of sediment from our reservoir. We will need to construct a confined placement area, but the next time we will need to construct a new placement area. So that means every time we will need to create new disposal areas. So this is why I say that practically this is not a sustainable solution. If we go downstream of the dam, then we need to be careful with the concentrations that we deliver to prevent adverse environmental impacts if we have very high concentrations. This can be achieved through water releases through our dam or through our power station. For example, it's always good to release dredged slurry downstream of the power station. On one hand, we do not interrupt the performance, the operation of our power station. On the other hand, we use the water that is turbined for the dilution of the dredged slurry. This reduces the concentration and mitigates the adverse environmental impacts that are relevant. There are also other possibilities, so to create a containment area near the riverbed downstream of the dam that will be practically cleaned with clear water releases from our reservoir. Again, the purpose is to control concentration. And all this is introduced, these considerations can be introduced in the costing of dredging operation, which is performed based on a unit rate for the unit cost of dredging. Please note that here this unit cost must contain the capital expenditures for procurement of dredging equipment, if that is the case. If it is outsourced to a contractor, of course, any overheads, profit of contractor must be considered also here in the unit rate. And we have also additional costs, for example, if we want to construct placement areas for the design and for the project management and construction management of dredging activities. And we sometimes, if we place the material in upstream, in upland disposal areas, this material can be reclaimed for beneficial services. For example, sand and gravel can be used as a construction material. Silty sandy material is good for agriculture. So this is something that might give an additional revenue benefit to the dredging operation. If usually, so the unit cost must be obtained based on experience from similar projects. As a preliminary assessment, if this information is not available, so we have implemented some guidance from a basic dredging cost model that has been developed by an American dredging company, and which provides indicative unit rates for different components of the dredging activity. As well as for the additional costs. Here we are considering a unit cost of dredging of $3 per cubic meter. This would apply to hydraulic dredging, downstream direct placement. And so let us, here at this point, I would like you to try different inputs, see what is the reaction of the storage development, and perhaps let us, after a few minutes, discuss about these results. I will, sorry, I will return in 5 minutes back, and then we can resume with the training, if that's okay with you.
Yes. So thank you, Nicholas, for that announcement of the break. We'll take 10 minutes, Nicholas. Will that be okay, or 5 minutes?
Well, let's do 10 minutes. If that's okay.
Yeah, let's do 10 minutes break. Yeah.
All right. Thank you.
Thank you.
Hello, Nicholas, are you there?
Yeah, I'm here.
Yeah. Are we good to go?
Yeah, from my side. Just trying to answer in the meanwhile a few questions I see in the chat box.
Sure. Okay.
It's possible. Let me just perhaps just complete the sentence.
Okay, sure.
Okay. So who would like to perhaps give some first impressions how the model reacts for dredging? Otherwise, I will continue speaking, so I don't want to do all the talking. Actually, I was planning to do less talking than what I do today.
Please raise your hands. The first two will be given the priority. We don't see any hands.
We don't see any hands. So I continue talking. So first, let's see what happens if we say that we want to remove.
Nicholas, I think Mr. Subhash Thapa has a question.
Okay.
Subhashji, you can unmute yourself.
Thank you, Mr. Sivan. Actually, I wanted to share like what I got while running the model as Dr. was suggested. So from my input parameters, what I can see is that if you change the dredging from just the specification of deposit removal capacity to sustainable solutions, then you will have a far better results in the operation or the service period of the reservoir. Can you hear me?
Yeah, I can hear you.
Yeah. And while changing the dredge slurry concentrations, it really does not matter. Like it does not really show any changes. But what we can see is that if we opt to use the sustainable solutions with technical constraint, and then increase the frequency of dredging also, then still you will have a very good operation period or the service period of the reservoir. But if you just go with the specification of deposit removal capacity, and if you just increase the frequency of dredging operations starting from year 1, and if you just put frequency of the year as number 2, then it directly drops the service lifetime of the reservoir. So I just got from that running of the model.
Thanks. That's very good insight. Let me just build on this. So what you said. So let's see here the example. So I will do this. Let's do this let's do this 3 million cubic meter starting the first year. Okay, so from the first year of operation, we start removing 3 million every year. And we go to results. So first of all, the gray line shows the no action. What we can see is that we have clearly an extension of the reservoir lifetime and makes sense. Look, let's go now to the sediment balance. This was also one of the questions we had yesterday. So the orange is the sedimentation. We see that initially we have a sedimentation close to 4.5 million cubic meter. The yellow is the deposit removal. So out of this 4.5 million sedimentation, we remove 3 million every year. So this is the reason why we have the extension of the reservoir lifetime. If we did not implement dredging, every year we would lose 4.5 million of our storage capacity. Now we have a sedimentation of 4.5, but we remove 3 million every year. So that means the net sedimentation that we have is 1.5 million compared to the 4.5 million. And this is the reason why we have this extension of the lifetime. We see that we don't have any significant impact on the trap efficiency of the reservoir. But what we see is that we have a significant impact on the economic performance of our reservoir. So now we have a performance 290 million. And here we have 215 million. So in this scenario, so actually dredging improves the performance of our reservoir. Okay. Now, if we go to input and say we do the cost is 5 million, is $5 per cubic meter, then of course we can anticipate that the economic performance of our reservoir won't be so good. So now we see that the long-term economic performance is 90 million. So again, compared to no action, we see that we still have the longer time period, but now we pay too much for sediment management. So this is my key takeaway here, is that dredging, of course, is very sensitive to the economic aspects. So, and the cost depends on many parameters. One of this is where are we doing the placement of our material. Generally, look, if we go in upland areas, that means not downstream of the dam, generally we can expect that dredging is going to be more expensive because we will have longer pipelines for the slurry. Most likely it will be the case that we will need booster stations in order to pump the material to the placement areas. So this increases the cost of dredging. If we have the possibility to release the material downstream of the dam, and so to control, of course, also the concentrations downstream in order to avoid adverse impacts, then this is going to be more economic because we have shorter length from dredging area to the release of the dredge slurry. This means we need shorter pipelines, which is one of the parameters that drives the cost for dredging. And it will be less demanding for energy consumption, regardless if we have a diesel dredge or an electric dredge. So this is something that we need to consider, that the disposal area plays an important role in the overall performance of dredging, especially the economic. Now, as you said, if we select here, Subhas, as you said, if we select sustainable solution and say we implement this after 20 years, we see that in order to sustain the storage capacity at the level that we have after 20 years, we will need to remove 4 million every year. This is a first indication. And if we go to results, we see that here is the point where we implement dredging. And if we remove 4 million every year, approximately, then we can sustain the storage capacity. The key takeaway here is that, look, here you can specify when you would like to start with dredging. And if you press sustainable solution, it will tell you how much sediment you must remove with dredging this year. The other question is, okay, say that I have a dredge equipment and I want to remove, I want to specify my dredging equipment. I want to see what will happen in my reservoir if I remove 3 or 2 or 5 millions every year, and I start year 5. This way you can see what is the response of the reservoir. Okay. Again, we have same plots for optimization. This looks much more complicated than the previous plot for the catchment management. So here what we see is that with dredging, in that case, it is better to start early and perhaps not perform very frequent. Now I would like to move to, I told you that tracking is very similar. The main difference to dredging is that we have significantly higher water losses. Let me go to results. Here we say that we will remove every year, say 3 million. Okay, starting the 10th year, we will perform tracking every 3 years. And here you need to consider that in order to perform tracking, we must empty our reservoir, keep it dry for a duration of the earth moving works, so that we have the earth moving equipment entering our reservoir and removing the material. So this is the water losses for dredging, for tracking are significant. This is something that we must consider. And usually tracking is also relatively more expensive than dredging, depending of course on the amounts that we need to remove. So we go again back to results. And here what you see is that after the 10th year, actually the year when we are performing tracking, we generate practically zero revenues. Exactly because for the biggest part of the year, we need to have our reservoir empty. That means the water inflow during this period is released downstream and cannot be used for beneficial uses. Okay, and of course you see that we have a very bad economic performance here. With hydrosuction, look, here the main constraint that we have is what is the available head, because this is used for the excavate, for the removal of sediment deposits and the release downstream of the dam. So here the performance cannot be specified by us, but it depends on the length of the pipeline that we have from the dredging area in the reservoir to the outlet of our pipeline, how many pipes, the diameter of the pipes that we are using, material, the losses, and what is the available head. This is calculated with an empirical method that has been presented by Hotchkiss in '95. There are also different methods to calculate the performance of hydrosuction. And here we see that actually we can remove, in that case, approximately 1.2 million cubic meter per year. This is the result of the internal calculation. And if we increase the head to 140 meters, then we see that we have a better performance of the hydrosuction, because we have more gravitational head for the siphoning of the sediment deposits. So here we have one parameter. We assume that hydrosuction will be performed on an annual basis. So that's why we have this plot for the optimization. And here we see that actually hydrosuction would be optimized, so approximately after 20 years of operation. The reason for this is that actually the sediment delta by that time would have approached closer to the dam. So that means we would have more availability of sediment deposits in shorter distance from the dam, and hydrosuction would be more effective because we have shorter distance between top delta foreset and release of the discharge pipeline. Of course, this depends also on the type of gravel, on the type of the sediment deposits. It's easier to remove sandy material than to remove gravel material. So at this point, I would like to, if you take again 5 minutes to play a bit around with tracking and hydrosuction. We discussed thoroughly about dredging, so that you get an impression of the reaction of the reservoir, both the sedimentation development and the economic performance to different parameters. And then let's discuss 2 minutes about this, 3 minutes, and then we move with the other alternatives.
We have 30. And articles in detail, and often
Dil, I'm not speaking now, so just was giving us some time to change the parameters to see the response of the reservoir. Okay. So anyone who would like to share impressions and feedback on what is the response of the reservoir to different options regarding the specification of hydrosuction or tracking?
You can switch on your video and answer. Otherwise, you can raise the hand in the chat box. You just need to, either one of them you can do that.
Okay. Would suggest, let me just say a few things. Look, with tracking, again, we have the same logic as with dredging. So we can answer two types of questions. So what will happen if we start with what is the amount of material that needs to be removed during each event in order to have a sustainable, so that means so conservation of our reservoir storage after the time we implement this alternative, and what is the development if we remove during each event a specific amount of sediment. So I would not say that there is a big difference, and the logic is more or less the same. The important difference is that tracking, it's associated with higher downtimes, downtimes and outages, so meaning more water losses and revenue losses than dredging. Now for hydrosuction, so say that we have 100 meter available head, and so we will implement dredging hydrosuction after 10 years. We go to results. So we see that we are removing close to 1.2 million cubic meter during year after the implementation. We have insignificant, not important water losses for hydrosuction, and we have an extension of the reservoir lifetime from 38 to close to 50 years, and then we maintain this residual storage capacity of 1.2 million. This is the amount that we can remove every year. Now, if we go to input and we say that we have 120 meter head and we use 2 pipes, you see that we can remove 3.7 million cubic meter per year. And we go to results. You see that we have a different picture. So hydrosuction is much more effective. The reason is that we have more head, so actually more energy to remove material. And we have doubled the pipelines that are used. So these are the key parameters. Yeah, please go ahead.
Yeah, I have a very quick question. While using this hydrosuction, one interesting thing what I found out is that I also wanted to increase the number of pipes so that the sediment could be extruded, but it does not allow installing more pipes than 3. So is there any reason? And once you install greater number of pipes, the long-term storage capacity significantly increases.
So it becomes much more effective with a larger number of pipes.
Another thing is that in the optimization chart which you have also inserted there, it shows the most optimal time for the implementation of hydrosuction is around 20 years. Correct? So is it due to the capex, capital expenditures related to installation of hydrosuction infrastructures, or maybe are there any technical reasons? Because I found that very interesting.
Look, here what we say,
Okay,
given this in this example, is that the pipeline length for the hydrosuction is around is 2 kilometers. So if we install it the first year, our reservoir has a length of 3.5 kilometers, if you remember. So if we implement hydrosuction from the first year, so we can remove deposits that extend practically 2 kilometers upstream of the dam. But the first year of reservoir, we said that delta progresses from the reservoir headwaters toward the dam, right? So that means the first year of operation, actually at the distance of 2 kilometers from the dam, we don't expect to have deposits because the deposits are located further upstream, close to the reservoir headwaters. After a few years, and as the delta progresses, then actually we are removing sediment effectively. So practically what this shows is that there is no need to implement so early hydrosuction in a reservoir with a distance of 3.5 kilometers, because we don't have sediment to remove at the distance of 2 kilometers. If we wait until the delta reaches the area, then it is the time when hydrosuction becomes effective. I hope this answers the question. And the
I got you.
And the other point, is, you said, so with the 3 pipelines, that's a good point. Actually, we followed this method that was implemented, that was developed by Professor Hotchkiss in the USA for the assessment of the efficiency, and this was also so implemented in the first version of RESCON. Practically, to be honest, I believe that it's logical to install also more than one equipment. So I would say that it's possible to have more than 3 pipelines. This is one limitation here in the model based on the theoretical basis that was used in the model, but think that actually it would be possible to install more than one hydrosuction device, so dredging equipment. In that case, what I would do, I would increase practically the diameter of the pipes, since there is no possibility to increase the number of the pipes, until so you would have a comparable performance. So as a way to work this around, instead of having here 3, say you want to have 2, 3 have a deposit removal capacity of 5.6 million cubic meter. Say you would like to see what happens if we have 4 pipes. This would be an increase of 33% approximately. This would be 5.6, say it would be 7 million or 7.5. You could try to see what happens if I increase the pipeline diameter. So do it 0.65, just an example, so as a way to work this around. Okay.
Thank you.
So then we go to flushing and look here, the controlling parameters, how aggressive flushing will be is what is the flushing discharge. So here it's important to point out that we are talking about reservoir empty flushing. So that means we will empty our reservoir till this elevation, the water level at dam during flushing. This is going to be the invert of the flushing channel that will be scoured in the sediment deposits. Here, this is a typical cross-section of our reservoir. And so 180, here is the elevation where we have the drawdown during flushing operation. This is the average discharge during the flushing event. Okay. Here we specify what is the duration for flushing during drawdown conditions, how much time it takes to empty the reservoir. And here we specify also parameters that can help us calibrate the flushing assessment. And so, for example, if we use this here, this parameter 2, we see that we have a much wider flushing channel. This can be used in case we have experience from previous flushing events and can help us calibrate the performance of the estimate, can help us calibrate the estimate of flushing. Other controlling parameters are the type of sediment deposits, how difficult it is to remove the sediment deposits. Again, we need to specify the costs for implementation and operation of flushing. Here, what I want you to consider is if we have an existing reservoir that doesn't have a bottom outlet, then here, it would be necessary to write that if we want to perform flushing, we need to retrofit a bottom outlet in our dam. You can understand that this is a very expensive story, to say $100 million. So here would be the point where we can specify this cost. Now, if we have a greenfield project that has a bottom outlet embodied in the dam structure, then, for example, here it is not necessary to add this cost. But generally, this can be used to evaluate different options at early project development phases. For example, here, if you are studying two different options for the discharge capacity of the bottom outlet, if the one is more expensive, here would be an area where you could compare the two options, the one with a small bottom outlet, the one with a big bottom outlet, and how this affects the flushing operation through the flushing discharge, and of course, how the respective costs affect the economic performance. The last step is again to schedule, to implement to specify the flushing schedule. If we go to results, we see that here, after 5 years, we start performing flushing. And after a while, so we perform flushing every 3 years. Here I must point out that here this assessment has been improved. So in the final release, the flushing assessment will be improved than the one that we have here. And here we are having a known bug here in this version is that with existing reservoirs, flushing is not working well as in the multiple techniques. So this is what we have improved in the version that will be released the coming days. The principle is again the same. So here you see perhaps a little bit difficult to identify the deposit removal. And yesterday we had a question about downstream impacts. Here, what I would like you to consider is that, look, in very short time, here we said, okay, perform flushing every 3 years. In very short time, we release downstream a big amount of sediment deposits, here in that case 9 million. Here you can imagine that we have the sedimentation that occurred during 3 years within the area where flushing is effective, and we remove the sediment deposits in a very short time of 1 day. You can imagine that this creates an overloading, a sediment pulse downstream, that the river it is very difficult for the river to manage. So this is why flushing requires very careful planning. And actually, so we must consider how much water will be released downstream, how often flushing will be performed, and we try really to reduce the amount of sediment deposits removed during this very short time period in order to reduce the concentration that is released downstream. And as said, there is a lot of work done in different countries, especially in Switzerland and France, on environmentally adopted flushing, which is combined with sediment monitoring, and the purpose is to avoid exceeding specific sediment concentration thresholds that might be harmful for the aquatic population downstream of the dam. So at this point, I would like that we go to sediment routing techniques. And so here we see sluicing. Let me start very shortly to start with this. Here, sluicing is more aggressive the lower the water level drawdown during sluicing. Sluicing means that we drop the water level in our reservoir. This has as a result that the flow velocities in our reservoir are higher. And so that means that the trap efficiency during this period is lower and we have less sedimentation. So this is how sluicing works. It's important to try not to confuse with flushing, because in both cases we have the water level drawdown. With flushing, we try to reinstall free flow conditions into our reservoir. So, and we try to scour, to remove, to remobilize sediment deposits that occurred before flushing. And with sluicing, we try through this water level drawdown to increase the flow velocity in our reservoir, but the purpose is to keep the incoming sediment in suspension through the higher flow velocities and to release them downstream. So actually, we try to reestablish the sediment transport continuity during the high flow period in our reservoir. So this is the key controlling parameter. The duration of sluicing affects what is the amount of sediment that arrives in our reservoir during the condition of increased flow velocities. So this is why also a controlling parameter for the efficiency. Again, we need to have an assessment of the respective costs for the implementation. For example, if our reservoir doesn't have a gated spillway, then actually it's not possible to control as we would like the water level and to have these controlled hydraulic conditions in our reservoir. In that case, we would need to retrofit a spillway that would be suitable for sluicing operation. And again, we need to specify the schedule. look for bypass, it is the same principle that we are applying, and density current venting. At this point, I would like that you take a few minutes to change parameters to see how we react, and then please let us discuss shortly about the reaction of the reservoir to different combinations of parameters for sluicing, bypass, density current venting. Okay, shall we perhaps go through sluicing? Professor Sharma, you made some very interesting points on dredging. Let us, in a few minutes, would you like perhaps to summarize your points? Because I think they are very interesting for the dredging assessment.
Well, thank you. There is a little disturbance in the surrounding. There is a wedding going on, but still, if you hear, like I had research undertaken for about a decade in Khimti hydropower project, where the main problem was emptying the desilting basin, and that they were doing during dry period, and that was causing an ecological crisis of the river downstream for several kilometers downstream. The way, as you said, the river cannot adopt this. The way river was behaving, there was massive eutrophication, and there were even stretches where the ammonia gas and methane gas were released. So impact may be worse to that extent. So in order to prevent that, I recommended that emptying of desilting basin be done when there is a high flow downstream, and that is during peak monsoon period. And they have taken that recommendation in practice, and that has helped a lot. And other advantage was at such during dry period, the electricity demand is high and availability of water is low. So that was not in recommended practice. So if we do both during monsoon, on one hand, there is high flow, and on the other hand, this will limit the ecological consequences. So that was the whole idea behind why I said, if this could be incorporated in this model for we in the Himalayan river system, this will be one of the acceptable model on that ground.
Mm-hmm. Professor, thank you very much for the intervention. Very interesting, as you say. So the downstream impacts are important aspects that must be considered. Unfortunately, in RESCON, so the seasonal variability on flow on RESCON, on dredging assessment is not considered. But this was, if you remember in the presentation, one point, engineering judgment is required. So it's a combination of sedimentation assessment, downstream impacts must be considered, what is the hydrology prevailing. So, and this, of course, this model provides some indication on the amounts. When we go to downstream, then all what you mentioned must be considered. And there is the engineering judgment, the sound engineering judgment is very important. So for thank you very much for your comment in this lecture.
Yeah, thank you for responding. It's really helpful.
Okay. So now when we go to sluicing, I see there was a comment that if we had a specification of water level during sluicing of 100 meters. So this should generate an error in the assessment. So meaning that this is not an acceptable input. The reason for this is that actually the lowest point of our reservoir, so the riverbed elevation at the dam axis, is at 130 meter above sea level. So that means we cannot have a water level drawdown lower below 130. So I hope that this explains the reason for the generation of this error. So at this point, anyone who would like to give some impressions from the performance of the reservoir to different constellations of for different parameters affecting the efficiency of sluicing or bypass? I see that you prefer to set the questions in the chat. That's okay. Let me just perhaps give just a comparative evaluation. So say that we have a water level during sluicing of 225. When we go to results and we have a duration of 5 months. First of all, what I would like you to see is that the first years, sluicing is not very effective. Here, try to imagine that actually we have an empty reservoir. We lower the water level during wet season. But what we are doing now, at the same time, our dead storage is relatively empty. So what we are doing now is we are doing a rearrangement of the sedimentation, moving sediment from the delta to the deeper parts. So for this reason, we don't see any significant impact on the active storage and the storage development. And we start looking the impact compared to the no action after a few years, when actually we have filled our dead storage. And at that point, we start protecting more the active storage. The other point that I would like to highlight in the economic performance is that we see that here we don't see water losses for sluicing. The reason for this is because if we go back to geometry, first of all, see that the water level during sluicing is at 225 meters above sea level, and our minimum operating water level, it is at 224.5. So that means during sluicing, we can run our turbines. Now, if we go to sluicing and we say that, okay, what will happen if I do a very aggressive water level drawdown at 180 meters above sea level, we go to results. We see that sluicing is much more effective, but at the same time, we see that this affects a lot the economic performance of the reservoir. The reason is that for 5 months, actually the 5 wettest months of the year, we're saying, okay, I will operate my reservoir below the minimum operating water level. I will not generate. I will not be able to store water for the dry season, since we have the storage operation. On one hand, I can, okay, sustain the storage capacity, but on the other hand, I cannot use the water that arrives during the sluicing period for the beneficial services. So this is something that needs to be considered. This is the compromise during sluicing planning. What is the water level that can, on one hand, protect my storage, and on the other hand, cannot affect significantly the economic performance of the reservoir. Same considerations apply also for bypass. So here the duration of bypass is a very significant aspect, and the amount of the water inflow. Okay, that the efficiency of water inflow diversion. We will see this tomorrow during the example that we will run on the picking operation. At this point, I would like to return back and we go again to hydrology. I would like to show you how we can retrieve data for the climate change analysis that we will run tomorrow. So what we can do, is in Google we write World Bank Climate Change Knowledge Portal. The first link, and then we go here, it is the first page. So please go to watershed, select a watershed that is relevant for our project here. And then we go to climate projections. So here, what we need to do, here you see different types of information. What we need for the RESCON 2 analysis is, first of all, we need the change in mean temperature and the change in precipitation. Come on, we'll change this again. So the precipitation percent change. Okay. Let's do the temperature. Then we need to select what time period we would like to analyze, say after 40, 50 years from now, 260, 2079. Here, please select the change. Then we need to select what scenario we would like to investigate. And here, unfortunately, we will need to go one by one. And we will need to download this information. So in the previous version, we had all the information in one file. Here there is manual work that needs to be done. It will take approximately 1 to 2 hours to collect all this information because we need to go through each model, GCM. So we collect the, say, the HLS file. We open this. And here is for the model that we downloaded. So here you see the name of the GCM model. The average change of temperature. We can calculate the average change of mean annual temperature. And this is the information that we will need to implement here. So we will select the model. We can write here the model and then the expected change in temperature for the emission scenario that we selected and the time period that we selected. This is practically not compulsory input, okay? But this is the way that we can, and trust me, this is the easiest way to find this information. There are many other data sources. And of course, there is also a lot of modeling that is conducted on each country. So if you have site-specific projections, it is better to use these projections for the project site. If this information at early project development phases is not available, then you will need to, one possibility is through the climate change knowledge portal of World Bank. But unfortunately, this needs to be done manually, GCM after GCM, and then type this here in this table. And this for temperature and for precipitation. I know that previously this could be done within 5 minutes. Now it will take 2 minutes. It will take 2 hours. In any case, it is what it is. So things also changing. I admit that in the meanwhile, when we're developing the model, things have changed many times. But this is the way to proceed forward. What I would like to show you here is that, okay, we downloaded the information on temperature and precipitation. And then we can come here and say if you have hydrologic model of the catchment, you can say that, okay, if I have an increase of 1.3 degrees Celsius and an increase of 23 millimeters per year of precipitation, then I will have a reduction of 2.35% of the runoff, because I will have more evaporation, evapotranspiration in my catchment. If you have a model and you have this result, one possibility it is to type this here. So I will have a reduction of 5%. Okay, so what I want to say is that this information is available from data sets freely available. This can be inserted even if there is a hydrological model from the catchment, but if it is not available, then we have implemented Gardner's empirical assessment from 2009. So let's do this -20. You need to type, double click in order to type in this table. You write 3% and then you press enter in order to be accepted. If you don't have this information from site-specific models, then it's possible to use the empirical assessment from Gardner. And you see that this table is filled automatically, giving the response, the hydrological response, based on the specified temperature and precipitation change for each GCM. Two possibilities: either we have our modeling done, we specify manually the hydrological response. If not available, a preliminary assessment through an empirical equation. Same applies also in for the temperature and so for the sediment, for the future sediment yield conditions. This input here you cannot double click here because this has been specified earlier in the hydrological climate change data. But what you can do is you can insert here, if you have a model, catchment model for the upstream catchment, you can calculate, insert here manually the anticipated impact of climate change on sediment load arriving at the reservoir. If not possible, if not available, here you can insert some input that is introduced in the empirical equation that we have implemented in RESCON, and you can obtain an empirical assessment of the tentative and preliminary of the impact of climate change on sediment load. As you can see here, for instance, you can consider impact. You need to compare the historic with the future conditions, and it is a relative assessment. So what we do is we calculate with empirical equation the historic, for the historic conditions, the sediment load. We calculate for the future conditions, the sediment load, and then we say, okay, so we see an increase according to the empirical equation of 30%. That means for these conditions. So that means we take the sediment load that we have specified and we increase it by 30%. So this is how it works. And tomorrow we will go through this climate change analysis to see how we can see how sediment management can be analyzed as an adaptation strategy to climate change. So with this, I think that for tomorrow we are going close to 9 p.m. Professor, you have also a wedding. I don't know if you have to attend, if you go there.
Thank you so much, Nicholas. That was very informative and good one. Hope all the participants benefited from the training today. And we are exactly on time. We still have 4 minutes if there is any question, a couple of questions.
First of all, I would like, Sunita, is it possible to keep the meeting a little bit for a few minutes longer open, so that perhaps with a few colleagues who faced difficulties with RESCON, we could go through it for me to have a look? What is the problem?
Today?
Yeah, otherwise, please let me, I can share a Teams meeting.
No, that's fine. I think we can still wait for a few minutes. And then if there is like any issue with any of the participants, yes, please unmute and then maybe share their queries.
Okay.
So we have one query from Subhas Thapa. What is the watershed number for which we'll be downloading the data?
Look, I would suggest that we use this information that we have here. So this would be for the sake of not losing time for the manual insertion, so input of the information. So this would be the temperature and the precipitation that you see here in these files. Let's use these climate projections. But as an exercise, if you wish, I would suggest that we go to climate change knowledge portal and we use the watershed 104 or the watershed 103. And I think that watershed 104 would be more representative of Nepal conditions. Is this right?
Well, I doubt if 104 would be representative. You know, you are referring to Western Ghats. Yeah, if you go further north, minimize, and then which one is this now?
This is 101.
Yeah, this is again looks like lowland. Could you minimize a little bit? Yeah, this is again 99.
I think 99 could be okay.
Yeah, it looks like 99 would be quite close to Nepalese terrain. Yeah,
It covers more of our area and then the possibly.
Yeah.
Because I guess so 92, so averaging here would be really.
I think 92 is too much, so it's too much
we
we cannot use that one.
Chinese.
Maybe it is, yeah.
So the 179?
179 is too far.
Yeah. Okay, then 99.
Yeah, I think 99 would be okay.
Yes.
99 should be okay because 179 again is a different territory. You're covering Southeast Asia.
Okay. So, whoever is interested, if you would like to try to download the data, I said, please, we need this in the format that you see here in this table. So the change of the mean annual temperature in absolute numbers and the change of precipitation in millimeter. Okay, we will need to process this and then we can go through together tomorrow to see how this is introduced into the model. If you're okay with this.
Yeah, we
I would like to see how we are also with time tomorrow. So actually to try to see as much as possible from the assessment and to see also the climate change analysis, the results. There is quite a lot to discuss there. And we see so also with time, so we can discuss also several days. Let's try to take the maximum from the 9 hours that we have.
Yeah, we have the same time tomorrow from Nepal time 6 to 9. Yeah, but that will also include a closing session and also certificate distribution.
All right.
Briefly, yeah. So any more questions, Nicholas, from anyone? Or any remarks, anything? So Sanita has ISMO database also has some climate change scenarios available for basins in Nepal. And then the link is shared in the message. from regional database system, RDS.
Sanita, tomorrow perhaps would you like to take a few minutes to guide us through this the ISMOT database?
I think that would be great.
Yeah.
Sanita, do you agree?
I have to check actually, because I have not used the RDS myself, but I know that my teammates have set it up. But I can check with them and see if they have a slides or anything on using the scenarios. Then I can share whatever information I find from them.
Sanita, see if this is possible. So it would be great. Just a few minutes, so a very short presentation, because the more, you know, localized the information, the better, of course. So,
yeah, I think there's been a few projects at ISIMO that's looked at global climate models and regional climate model data sets. So there's definitely work being done. I can email the organizers if I manage to find something that I can present in a short time.
excellent. Okay, so I think we're good for today. Again, Sanita, if you can stay a bit longer, so to see, I think you had one question, so one issue with RESCON, so that we can go through, and also a colleague. Give me 1 second. So if someone had an issue with RESCON, if you can stay a bit longer in the session, and if you can share your screen, so for me to get a better understanding and try to find a solution and to communicate also with the programmers. So, all right. For the rest, thank you very much again. So I mean, to be honest, I'm amazed by the quality of the questions, the level of the understanding. So it's not something that you meet. So in training events, so well done. So thank you very much. For me, this is really the best training so on the RESCON and sediment management I have ever done. Thank you very much and see you tomorrow.
Thank you. Thank you.
Thank you so much, Nicholas. Thank you all. Good night.
I believe you hear the nice wedding music in the background.
So tomorrow, some photos, Professor, from with you dancing.
We can't hear yours, Subodh sir, but we also have another wedding at my back. So.
Really? There are 3 weddings going on today. Anyway, thank you so much.
Thank you so much.
Thank you so
Thank
much.
you. So Nicholas, we do not have other, I think, remaining queries for you. Yesterday we had few, but today we do not have anyone because you have already responded to all the queries in the chat box, right?
Yeah, tomorrow at the beginning, so we can, we'll check if something is didn't answer. I will ask also tomorrow. So I did my best. I hope that I answered most of the questions, but in case something has remained unanswered, so perhaps tomorrow you can.
Yeah, no, I cross-checked again, and I think you have responded to all of the queries and also the comments. Yeah. Okay, so thank you so much. It might be very tiring for you.
It's look, I was hoping that the participants would do most of the talking, so but it's better to